So welcome back to this series of videos on MPLAB Harmony 3, and what we're going to do in this video is have a look to see if we can improve on the clock speed that we're using. Now, out of the box we were just using the 8 megahertz clock speed, which is okay for doing sort of flashing LEDs such as we have here on the board, and also for generating our sort of very sort of boring text output. But what we'd like to do now is to have a look to see if we can improve the clock speed for the future, and we're going to be looking at putting on some USB in a future episode. But to do that, we need to get all the clocks set up internally on the board. So if we look at our project graph, you'll see here that there's not much here immediately showing what we're supposed to be doing. Now, there are actually multiple places that you can set up the clock. That's sort of quite common, and it's also quite confusing with Harmony. Sometimes you're actually better off with just one place to do it. But you'll see in the system clock menu, yeah, you'll see there's some clock configuration settings and various bits and pieces that you can do here. You'll also see, if you want to go really into bare metal, is you can do some few settings. And I think it's in this one. Yes, you can set some various bits and pieces here. There are also other fuses as well, if I can find them. But anyway, irrespective, we're not going to use any of those because they're a little bit well, you need to do a lot of referring to the data sheet, whereas there is another way. In the plugins, we've got something called the clock configuration, and now I said that this should be easier, but it's probably a little bit daunting when you first go in here and have a look at everything that's going on. So with that in mind, let's get started. Now, what I do happen to know is that this board that we're using here has a 12 megahertz crystal, if I can find it. Probably not be able to find it now, am I? Here it is. So you see here's a 12 megahertz oscillator which goes into the OSC in pin just here on our PIC. So if we have a look at it on the board, it's this device here, so Y2. So that's actually a 12 megahertz canned oscillator. It's not a crystal, it is actually a canned oscillator. So if we go back and go into our clock diagram, and we can change the primary oscillator to 12 megahertz. We also need to turn the primary oscillator on. Now there's three options here: E, C, H, S, and off. Off is what it originally was because we were using the free running oscillator on the chip itself. We weren't using this external oscillator. HS is if you're running a crystal. I have a vague recollection there's an errata issue with the crystal oscillator. That may be resolved now, but anyway, but typically in pretty much all the designs I've seen, they all use an external crystal canned oscillator here. Now, for whatever reason, microchip used 12 megahertz, and there's a reason for that. You have an option. The PLL for the USB, this is not the CPU's PLL, has only two possible options, either 24 megahertz or 12 megahertz. The FRC you just cannot use for the USB PLL. It's not accurate enough anyway. It's 8 megahertz too, so you have to use use an external crystal or a canned oscillator, crystal canned oscillator, such as we're doing here, and you have to select it to be 12 megahertz. You notice it went from red to black there. So yeah, if you're on 24 megahertz, it says there's something wrong there because it knows it's 12 megahertz coming in. And there we go. So 12 megahertz, that's our USB clock sorted. And the next little bit we want to do is, rather than running off of our FRC, we want to run off of a PLL to be able to run 200 megahertz. So we can, you've got two options here. You see there's a multiplexer. To use the PLL to get 200 megahertz out, you can either use the FRC or the primary oscillator. Now, if you use the FRC, everything's good. You can press that, if you notice what I pressed there, the auto calculate. It goes for 200 megahertz to start off with. You press apply, and there we go, 200 megahertz. And that did actually two things. Not only did it recalculate all of the correct settings here for the PLL to keep everything in the right range, the PLL itself, and the VCO on the PLL, and the post divider. It also made a change to the FNOS, because originally this was set to FRC div. You might not have seen it, but that's selecting the FRC. Now, or FRC div. Now we're using the SPLL, which is this. So there we go, 200 megahertz. Now you might say, well, why aren't we using the primary oscillator for this? It gets a nice, accurate CPU. Now I would say yes, absolutely. That would be what we should normally do. But if you try to do an auto calculate with the primary oscillator running, you'll notice that the best achievable frequency that is equal to or less than 200 megahertz is 198 megahertz. So you could do that, but I don't know. I just like my 200 nice round 200 megahertz. So let's go for the FRC and auto calculate on the FRC. There we go. Now it's interesting, on most other designs, the 24 megahertz external oscillator will actually generate a 200 megahertz system clock. So I would say if you're doing your own design with this chip, go for a 24 megahertz external oscillator, because it makes a lot of sense from the point of view of getting a USB clock and a 200 megahertz clock for your CPU. Next bit here is look at the peripheral bus clocks. Now, if I look at the data sheet on here, this is the microcontroller's chip. We're going for the maximum here. So you'll notice here that for the PB clock, not 4 or 7, so there's all the other ones, which is this here, not 4 or 7, 100 megahertz maximum. But for PB clock 4 and 7, so 7 is a CPU's clock, and 4 is for GPIOs, we can have 200 megahertz. So if we go back to here, you'll notice that PB clock, okay, 100 megahertz. So all these by default are all good. They're all 100 megahertz. Now, PB clock 7, which is for the CPU, that's set correctly. Now, PB clock 4, you'll notice that it's only set to 100, whereas in the data sheet, it says that we can go up to 200 with that. So let's set it to 200. You'll notice it goes red. Now, I think that's a bit of a hangover from an earlier time when I think it was specified that PB clock 4 couldn't go above 100 as well. But you're safe to go for 200 here. Okay, so that's all the settings for the clock. We've got a 200 megahertz system clock. We're good for our USB clock when we actually get to that stage. Next stage here is, let's see if we can set the wait states. Now, when running from flash storage, flash is not fast enough to be able to keep up with the processor clock speed. So there is a configuration item that we need to set here in the system, prefetch and cache configuration, and you'll notice we're disabled ECC, so no, we're not having any error corrected flash here, and the program flash memory wait states is currently set to 3. Well, let's have another look onto the data sheet. I happen to know this is on page 636. Here we go. So these are the required wait states for this process. So you notice that without ECC, between 140 and 200 megahertz, we need to have a minimum of 2 wait states. So if we go back to here, 2 wait states, there we go. the processor is set up for 200 megahertz, as we've seen before. If we zip over here we go. We've got the 2 wait states. Take that over, and everything should be hunky-dory except for one thing. If we look at the timer here, this used to be 250 milliseconds and it's now gone down to 167. So why would that be? Well, the reason is that the PB clock that is running this timer, in fact, if we go back here, I can't remember which PB clock it is. Let's have a look. There we go. It's PB clock 3 runs the timers, 100 megahertz. Now before it was running at 4 megahertz, which had a divider of 2 on the 8 megahertz. So it can't actually manage to do this 250 milliseconds. It's only a 16-bit timer. And even with a 1 to 256 prescale value, the best it can do with 16 bits, with the period register set to 65536, is 167 milliseconds. So how do we resolve this? How do we get back to our 250? So the answer to that is we go into our device resources and we can concatenate an additional timer. Now you can run a pair of 16-bit timers as a single 32-bit one. So you can do timer 2 and timer 3, timer 4 and timer 5, timer 6 and timer 7, timer 8 and timer 9. So we've already got timer 2 in here. Let's add timer 3 onto that. There we go. And I'm going to go into timer 2 and I'm going to say I want you to run as the master to the slave timer 3 as a single 32-bit timer. Now, one thing to note from here, which is a slight aside but interesting from the point of view of the sort of underlying technicalities, is that the interrupt now runs off of timer 3 rather than timer 2 when you've concatenated them. And you'll also see here that our time is back at 250 milliseconds. So, okay, let's do a generate, and hopefully everything works okay. That looks nice. Didn't see any errors. So let's go back through here. Looks okay to me. If you want to clear previous generates, you can do that there. There we go. That looks good. Okay, and let's go back to the project. Let's do a build. Very nice. Looks like that went through okay. And let's live dangerously and we'll have a look to see if this still continues to work. So I'm not expecting to see any changes here to the functionality. Because all we've done is change the clock speeds and the timer, but we just want to make sure everything still works. So there we go. And looks like it does. So we've got our flashing LEDs, and looks like our terminal is still working, so that's great. So that's how we set it up to use the maximum speed for the processor at 200 megahertz and still have everything running exactly as it was before. And in the next episode, we'll have a look to see how we can set up some USB, and look forward to seeing you there.